Welcome back, and in this lecture we're going to follow on from what we covered in the last lecture about the greenhouse effect and how important it is for causing the average temperature of the Earth to be greater when we have an atmosphere than when we don't. And why we're concerned about climate change is because of an enhanced greenhouse effect. And now we're going to talk more in this lecture about the structure of the atmosphere, the gases in the atmosphere, and how those gases have changed. And we've already heard that it's not all the gases in the atmosphere that are greenhouse gases. We're going to look at how these greenhouse gases have changed over the last 100 years due to human activity and how they're removed from the atmosphere. So let's now think about the structure of the atmosphere. And the atmosphere, when we look at it like in this background picture, is a relatively thin layer. The density of the atmosphere decreases with elevation. As you go up and up in the atmosphere, it gets thinner and thinner. And the atmosphere is divided up into multiple layers. This lowest layer of the atmosphere, the layer that's got all the clouds, all the typical winds, all the rainfall, all of the water vapor, is in this lowest layer we call the troposphere. And that's where temperature decreases with height. Above the troposphere there's a layer called the stratosphere, and in that layer temperature decreases with height in the stratosphere. That's where all the ozone is formed. And most of the ozone in the atmosphere is contained in this layer called the stratosphere. Now, what's really important is that there are what I described as long-lived greenhouse gases in the last lecture, gases like carbon dioxide. They're well mixed throughout the lower atmosphere, the troposphere, as well as the stratosphere. But their concentrations decrease as you go up and up through the atmosphere. Their concentrations and the density of the atmosphere gets less and less. And by the time you get right up into the upper atmosphere at heights of maybe 100 kilometers, the amount of air has diminished so much that it's, even at heights of the top of the lower atmosphere, at heights of 10 kilometers, you've got to have an oxygen mask, you've got to fly in a pressurized aeroplane to have enough air to breathe. Now, in the atmosphere, most of the constituents are relatively well mixed. The two that I've mentioned already, water vapor isn't well mixed. Its concentration depends on the temperature. But the two most common gases in the atmosphere are nitrogen and oxygen. They make up something like 97% of the composition of the atmosphere. Nitrogen's the most common gas, oxygen's the second most common gas, but they're not greenhouse gases, they're diatomic molecules. When we start to talk about the greenhouse gases, the most common greenhouse gas in the atmosphere is in fact water vapor, H2O. And the long-lived greenhouse gases, things like carbon dioxide, methane, nitrous oxide, actually only make up a very, very small fraction of the atmosphere. 100 years ago, the concentration of carbon dioxide was only about 0.03%. Nitrous oxide, methane, they're much smaller concentrations than that. But even though these greenhouse gases make up such a small fraction, they are very important in the energy balance in absorbing infrared radiation. So this now is if you like, an easier to read set of numbers for the composition, the concentration of these gases in the atmosphere. And as I said before, the concentrations of these gases is really important. The largest changes in these concentrations is the change in carbon dioxide that's occurred over the last 100 years. 100 years ago, the concentration was 280 parts per million. 2005, it was 384. And if we look at this, we can see that actually the rate of increase in carbon dioxide is around 2 to 3 parts per million every year. So that by 2013, the concentration was already 398 parts per million. This year, on average, the concentration of carbon dioxide in the atmosphere will be more than 400 parts per million. 400 parts per million corresponds to 0.04% of the atmosphere. Seems like a tiny fraction, but it's a very important component. The other important greenhouse gases in the atmosphere are water vapour, methane, and things like nitrous oxide, chlorofluorocarbons. We're going to talk about those in just a minute as well. It's important to understand that although there's a larger amount of water vapour in the atmosphere, and yes, water vapour is the most important greenhouse gas in the atmosphere in terms of its effect, human activity is not changing the amount of water vapour in the atmosphere. The amount of water vapour in the atmosphere is determined by the temperature, and it can increase when the temperature increases. Yes, it's an important greenhouse gas, but it's dominated or controlled by temperature, not by human emissions. And then, as I said already, the two most common gases in the atmosphere aren't greenhouse gases at all, nitrogen and oxygen. So if we look at how these gases have changed over time and how important they are for warming up the atmosphere, the impact of a gas in terms of warming up the atmosphere is related both to its relative impact in warming and its lifetime in the atmosphere. So if we look at this chart here, we've got a whole series of columns. The first one is how much was the composition in the atmosphere way over here in pre-industrial times, and the biggest fractional change has been in the concentration of carbon dioxide. It's grown by nearly 30%. The methane concentration has more than doubled. Nitrous oxide concentration has increased by about 10%. Biggest actual fractional change, if you like, is the change in chlorofluorocarbons, ozone-depleting chemicals produced by industrial activity. And then we can look at the concentrations, now in around the mid-2000s. That tells you the change in concentration. But their impact on the climate, molecule per molecule, depends upon how they interact with the infrared radiation, how much infrared radiation they absorb, as well as their lifetime in the atmosphere. And so the global warming potential in this column here is a metric that we use. This one here, whoops, let me get it right, is a metric we use for representing the relative importance of a tonne or a kilogram of that gas emitted into the atmosphere and the relative importance of that in terms of warming over 100-year time. And we measure the relative importance of these gases relative to a kilogram or a tonne of carbon dioxide emitted. And so the global warming potential of carbon dioxide is 1. Now, methane, molecule per molecule, is much more effective than carbon dioxide in absorbing infrared or heat radiation. But its lifetime in the atmosphere is actually quite short, only about 12 years. So when you take that into combination, very effective in absorbing infrared radiation, but not so long-lived as carbon dioxide, you get a net warming effect of 23 times greater warming from methane compared with the same amount of carbon dioxide emitted in the atmosphere. Nitrous oxide, long lifetime, strong absorption is even more important. And then the CFCs, or the chlorofluorocarbons, there's very little of them in the atmosphere, not so much emitted, but they have very, very big global warming potentials. So adding more chlorofluorocarbons would have a substantial warming influence. But fortunately, controls have been put on the use of chlorofluorocarbons, not because of global warming, but in fact because they also were important for ozone depletion. So when we combine the amount that's been emitted with the global warming potentials, we get the net impact just here of all these gases, their net impact in what's called their impact on the radiative forcing. And the radiative forcing is the change, the relative change in radiation due to these gases being added to the atmosphere. And in the next slide, we're going to find out a bit more about what radiative forcing means. And it's really the importance of these different factors, like changes in greenhouse gases, on the radiation balance at the top of the atmosphere. And it provides a common metric for comparing the impact of different changes in greenhouse gases or even changes in sunlight from the sun on the radiation balance at the top of the atmosphere. It's a measure of the radiation change at the top of the atmosphere since pre-industrial times. Positive radiative forcing means a warming influence on the climate, and negative radiative forcing means a cooling impact on the climate. And there are lots of assessments of what these changes have been. We can certainly measure the concentrations accurately of the changes in greenhouse gases or other factors over the last 30 years. We don't know as well what they were in pre-industrial times, but scientists have been assessing those from lots of different lines of evidence, and we can get good measures of the changes in greenhouse gases from their concentrations trapped in bubbles in ice cores in both Antarctica and Greenland. So this table, you don't need to know all the different numbers, but we can look at the colours and look at their relative magnitudes, shows the relative importance of a whole range of different factors and how much impact they've had on the climate system, how much change there's been since pre-industrial times, since about 1750 or 1800. And the biggest warming influence, the biggest red bar, is the impact of carbon dioxide increases on warming of the climate system. That's the biggest bar here. And notice there's a small uncertainty range because we're not absolutely sure of what that concentration was in pre-industrial times. The second biggest warming influence is associated with the increases in methane, and then the changes in chlorofluorocarbons here. That's the next most important influence, and then the changes in nitrous oxide. Notice that these are all warming influences from human activity. Then there's a range of relatively short-lived greenhouse gases that also impact, but they're short-lived. They don't have long timescales for removal. This set of radiative forcing columns is related to different human impacts on climate. This bar here and these ones here are associated with what are called aerosols or particles that are produced in the atmosphere by industrial activity. And the particles essentially are what we see in urban haze. When you travel over an industrial area or look at it from the distance, you'll see a grey haze. Or maybe in some highly polluted areas, you'll actually see a brown haze. That haze reflects sunlight and leads to a cooling of the climate system. But those particles also have an impact on leading to more clouds, and if they're dark particles like soot particles or brown particles, they will absorb sunlight and warm the atmosphere. So the direct impact of these particles is a cooling impact in terms of the radiation. If they're brown particles, it'll absorb sunlight and warm up. And down here is what's called the indirect effect from increasing the amount of clouds. The clouds, when they're increased, become more reflective and they will cool the climate system. There are two other factors, one other human factor that's included, shown here, very small, and one down here. This bottom one is the estimated change in radiative forcing due to changes in sunlight over the last 250 years. And it is very, very small, less than 10% of the warming due to carbon dioxide alone. This changes in albedo due to humans cutting down forests and planting agricultural land, essentially planting crops rather than having forests. Now, if you fly over a forest, it's typically dark. Fly over a grain field, whether it's wheat or rice or corn, it's typically going to look grayer or yellow. It's actually more reflective. So on average, agricultural land with crops or grazing land or grass on it is more reflective than a forest, and that means the albedo's increased, which means there's less sunlight absorbed. So this includes an assessment of all these different factors and how much they've warmed up the climate system. And this is the warming influence at different time periods. And what we see is there's been an increase in radiative forcing up to the most recent period. The radiative forcing is increasing due to increases in greenhouse gases in the atmosphere. We can now look at actually what's causing these increases. What are the human activities that are leading to increases in the greenhouse gases? And how are these greenhouse gases removed from the climate system? Well, let's consider a very short-lived greenhouse gas, not even in this table, and that's water vapour. Yes, it's the most important greenhouse gas. The major source is evaporation from oceans and from land surface and plants, and it's removed from the atmosphere by rainfall. And it has a lifetime of only a week, a few days. Now let's consider something which is much more long-lived, carbon dioxide. And yes, carbon dioxide has natural sources from the oceans and natural sources from plants. But there's, in addition, important sources from human activity, from burning fossil fuels, from land clearing, and from industrial activity. And these have led to major increases in the emissions of carbon dioxide into the atmosphere. Whereas the carbon dioxide in the natural system was in balance, now there's an extra source. Carbon dioxide is removed from photosynthesis, hard word to say sometimes, and that photosynthesis takes up carbon dioxide into plants, as well as into the oceans, where carbon dioxide is absorbed into the ocean waters. And carbon dioxide is also taken up into soils. When we think about the lifetime of carbon dioxide, the cycling of carbon dioxide between plants and the atmosphere, or between the upper layers of the ocean and the atmosphere, is about a 7-year timescale, but that's just cycling around. The long-term removal time for carbon dioxide to be removed into the deep oceans, or carbon dioxide to be returned into rocks, is much, much longer timescale. And it's typically 100 to 1,000 or even many thousands of years. There's no single lifetime. As I said, concentrations have increased rapidly, 300 parts per million 100 years ago to now nearly 400 parts per million. Methane. Major sources of methane from human activities include from agricultural activity, particularly from rice production, as well as leakage from coal seam gas and leakage from biological decomposition. Actually, rubbish dumps also produce quite a lot of methane. Methane is produced by biological activity on plants and other things, decomposition. And in particular, it's produced from what's called anaerobic decomposition, when there's not enough oxygen. Lifetime for methane to be removed from the atmosphere is typically about 12 years, and it's primarily associated with oxidation of methane with the hydroxyl radical, or the OH radical. So this is a chemical reaction that removes methane from the atmosphere. The concentration of methane has grown by more than a factor of 2. It's more than doubled in concentration over the last 100 years. Nitrous oxide, produced mainly by agricultural activity, by fertilizer use and other industrial activity and agricultural activity. It's mainly removed by chemical decomposition in the atmosphere. It has a relatively long time scale for removal, and it's only grown 10% in the atmosphere over the last 100 years or so. Halocarbons. Well, there's a whole range of different halocarbons. As I said before, the dominant halocarbons, chlorofluorocarbons, were used originally as very stable compounds for refrigerants, for propellants, but it was discovered that the chlorine in the chlorofluorocarbons actually depleted ozone. So they were banned, or their production and use was banned by the Montreal Protocol, and now new halocarbons, which don't contain chlorine, hydrofluorocarbons rather than hydrochlorofluorocarbons that don't contain chlorine, are being used as replacements. They don't destroy chlorine, but they actually have very high global warming potentials, and they've been increasing rapidly over the last few years as well. So it turns out that over a long time period, the hydrofluorocarbons, no chlorine in them, they're likely to increase rapidly over the next few years. So, in summary, when we want to look at the relative impact of different gases in the atmosphere affecting the greenhouse balance or even affecting the climate, we use this metric called radiative forcing. It measures the change in radiative balance at the top of the atmosphere. Different greenhouse gases have a different contribution, and we can use the global warming potential as measuring the relative importance if we emit 1 tonne or 1 kilogram of a gas, or we can use the net change in radiative forcing from that gas. But when we look at this radiative forcing, the most important long-lived greenhouse gas in the atmosphere is the change in carbon dioxide concentrations over the last 100 years due to human activity. Carbon dioxide emissions have the greatest warming effect through radiative forcing, and that's why most attention is being put on trying to control their emissions so that their concentration of carbon dioxide doesn't grow anymore.